All right, now we've got Mahmoud El-Ghazawi. He's going to talk to us about advanced surveying and ranging technologies, and then he knows all about it, so I'm going to let him have the mic.
Thank you so much, Chad. Just quickly, my bio, I forgot to add one line here that 127 hits on XWA page. So thanks to those 127. I'm Mahmoud El-Ghazawi. I've been part of XWA for many years, more than 15 years. I work for SLB almost 20 years now. I also worked for Sperry, Halliburton for some years, and I'm based in Bucharest, Romania. We're talking today about a case study, an actual case study of a well that we drilled that has been very challenging. I will go through the details of this well. What are the challenges that we faced, and what are the solutions that we came up with to achieve the well objectives. And you see the contents here. We're going to go through it in the coming 20 minutes or so. So this is an ERD well, long ERD well. And you can see here some details, and you see two wells on top of each other. So what happened in this case, we drilled one well, the green one, in 4 years ago. And there has been a problem in the production for some reasons, and the decision was taken to drill another well that is very close proximity to the first one, which is the blue well that you can see. And the well schematics, as you see there, we have a top section, and in this well here is 26-inch top section with 20-inch conductor. And then we drilled 16-inch hole down to 6,000 feet. And then we drilled the longest, I would say one of the longest 12.25 sections. And we drilled down to 25,000, one section. Sailing angle around 60 to 70 degree. So this section here is around 19,000 feet. It's pretty long, substantially long for 12.25 feet. And then we have the last section, the 8.5, focused from 25 down to 30,000 feet. Why do we say this is ERD and challenging? What you see here, this is a common nose chart. Most of you here are probably familiar with it. It shows the ratio between TVD and departure of the well. And typically, whenever we say ERD well, this is when the ratio is 1 to 2 and more. And you see here some color shaded. The two wells that we're talking about here and the wells that we drilled, is there a pointer? I can use that.
Why not? But it's not.
Okay.
All
right. So yeah, I can use this one. I think you can see a green and blue lines there, and they come through the extreme reach reach zone, right? So this is the TVD here. We're talking about 12,000 TVD. And this is a departure. It's around 25,000. The well, the TD is total 30,000, but the departure is around 25. And you see the ratio here, it's 1 to 2 almost. And it comes down here in this extreme reach. Very challenging to drill. We had a very tight target that we wanted to achieve. And the target that we wanted to achieve, we had a 50 feet TVD window that we wanted to land the well at the TVD at the end of this 12.25 section. Very tight. So typically for us as surveyors or drilling engineers, okay, very simple. We have a well plan. We start to select, the tool codes that we run, the error models, and we look at the target sizing and we try to fit and see. So in our case here, nothing is working. We cannot find a tool that will take us with an uncertainty less than 50 feet on TVD at this ERD well. So this is one of the main challenges. The other challenge, it's a very complex ERD well, a lot of wellbore stabilities, a lot of drilling, imbalanced drilling. So a lot of issues, and no one wanted to hear about additional challenge when it comes to wellbore surveying. I'm not talking about the tool we're going to run, but the condition here, anything that we want to run when it comes to wellbore survey tools, it should not add more challenging to the operation. It should not add more time to the operation. We should not take longer to take surveys. It's going to add more time to when it comes to wellbore stability. It's going to cause a lot of issues. So this was one key point. Any proposal that we do, anything that we add, it should not add any complexity to the drilling operation that is already extremely complex. And last but not least, we have already another well that we do not want for any reason to intercept, to collide, and we wanted to come up with measures to be able to drill this well, our well, that is in close proximity to produce from the same reservoir as the previous one, and to stay very close with 50 feet and less. If you start to think about separation factor, and all of you are very well versed in separation factor, at this 25,000 plus, we're talking about EUU sizes of 2 wells, and we want to keep our separation factor larger than 1 and 1.5 if you want to be more on the safe side. How challenging this can be. I'm sure you realize the challenge here. So now we start to think very, very simple. Okay, now I'm going to run one tool. Phil will agree with me that if I'm going to run one tool, and a lot of people here in the room, we use a field acceptance criteria for validation to know good or bad, and we rely on it. Can we only rely on the field acceptance criteria for when we run this tool? It's too risky. We cannot. So what do we do? First methodology that we're relying at here is survey redundancy. What do we mean about survey redundancy? We run an additional survey tool. You run an additional MWD, you run an additional gyro, you need to have another survey package in there. Ideally, you want to have a different physics. You don't want to have like 2 magnetics and compare to each other's. You want to have 1 magnetic, 1 gyroscopic, 2 different physics. At least you're able to nail down any gross errors when it comes to the, let's say, for example, declination error in the MWD. You can easily spot it. You run a gyro, or if you have a gyro drift issues or angle random walk or what's not, you're able to cross check when you run an additional tool. So this is number 1 when it comes to the survey redundancy. Now I have another tool in my drill string. I'm going to take advantage of this one. I'm going to combine these 2 surveys. And this technique is not new. It's something that has been discussed several times before. And we have members in the room today. They have a lot of publications and work on this one. Marianne, Adrian, and others. So we said, okay, fine. We run another tool. We have redundancy. We detect gross error. We combine both. We reduce our EOU, would allow us to drill closer and maximize reservoir production, and do it all in a safely manner while avoid colliding with the other well. And also, and now when it comes to the QC as a methodology, we look at each tool individually. You need to pass their own QC criteria. And all of you know, when it comes to the MWD, we're looking at the basics one, delta depth, delta earth magnetic field, and delta G. Similarly for gyro, whenever we run a gyro, we look at the drift or the earth rate, G also, and the latitude as the similar criteria that is more relevant to the gyro. We make sure both of them, they pass individually. And next step, how good of an agreement to each other they have. And there are common tests that has been run, and it's been run by most of the people here in the room. They're very familiar with it. And this is to see how good they agree with each other. The first test is a very common test, RIP. So I tried to spell it out for a reason. Some people will read it something else, like rest in peace. So I tried like relative instrument performance, that's what it means. And chi-square test and EUU overlap. Rep test, as you all know, we compare the inclination and azimuths. We look at the mean and standard deviations, and we have a tolerance to confirm they are within agreement from each other. And based on the results, if we see like the mean is off, for instance, we know there is a systematic error somewhere in one of the tools. We try to identify it. If we see like standard deviation is off, we realize that could be like some random errors that manifested itself somewhere in one of the tools. Then we have the chi-square, it's a more statistical test, and that's a good way to check. And in this chi-square, we look at the uncertainty of the surveys that we're running. And this takes into account the error model that we're going to use for each surveys to validate also. And the last test is basically a visualization test, the one that you can see here, to see if you have a full enclosure and if all of the are like really in disagreement. So we go through these steps. And they pass, great news. We have 2 independent survey packages, they pass, and we're confident they pass their own, they pass the agreement to each other. And then we move to the next level, which is, okay, fine, great news. Let's combine both of them. We'll have an advantage to reduce the uncertainty further by combining both. So the way that this is combined, and like I said, this has been discussed previously. I presented here several times, and I have an example here that shows it's more like a weighted average that we look at the different parameters and what is the accuracy for each parameter to combine. And what you see here, this is an example of the weighting function that is used for the MWD tool that is relevant to the Wellbore geometry. For instance, if you are drilling east-west horizontal, you will see like you're not going to have a lot of weight on your atoms here. This is what it says, where in the best case, if you have 2 tools are very equivalent in the top sections, you're just going to have half from here and half from here as an accuracy wise. So we use what like the methodology that has been developed, and there is a lot of publications on this one. Last one by Marianne on practical implementation of this combination methodology. And then we create the combined surveys, MD Inc. as, like based on the trajectory that we combine, as a new survey listing that we use as a definitive surveys. And also we do it along with the error model that is used from the combination of the 2 error models from the 2 different surveys. If I'm running MWD, it depends. If you're running MWD with some corrections on top, like in-field referencing, multi-station analysis, SAG, this is the error model that we use. For running the other tool, it depends what are we running. It's solid state gyro-while drilling or prop gyro, whatever it is. We use both and we combine both to come up with one IPM file that can be easily ingested by any common error analysis software out there. So this is a methodology that we talked about. When it comes to the Wellbore positioning, the position of our Wellbore trajectory. And in a little bit, I will talk about the relative position, which is the ranging piece that we had to do in the 8.5 in order to stay, to drill safely the lateral closer to the old lateral well. So what are the tools that we used for us? Can you think of how many tools we try to combine here? Any guess of the audience? Oh wow, that's very aggressive. Okay. Anybody else? Okay, that's fair. So we started with RSS. RSS tool will have a survey package. We know that we have a good inclination we get from the RSS. So that's one information that we get, and this is at bit inclination that we use. And then we run MWD. All of us we run MWD. So the first thing that we do, we get the inclination from the RSS. We get the MWD. We run the correction on the MWD, IFR, MSA, SAG, along with the SAG on the ink from the RSS, and we combine both, and we end up with the first surveys, that is the dual ink, IFR, MSA, SAG. So these are two tools now, RSS and MWD. And then we added a solid state gyro-while drilling on the BHA as well. Give us additional QC, as I explained, for gross error detections and also for positioning accuracy to reduce the uncertainty of our position. So this is while drilling, the 12¼ section. And if you still remember, we talked about 19,000 feet of a section that is very long, ERD, TVD, we're talking about 10,000+ feet. And we have a departure that is very, very high. We TD the well, and this was not, like we TD the section of the 12¼ and this was not enough for us. And to have the required accuracy for us for the to hit the tight target, and we had to drop as another gyro, solid state gyro. The beauty about this solid state gyro that is not just one package, it's actually dual package gyro. So think about it, you dropped two gyros in the BHA at TD of the 12¼ So now we have the RSS, we have the MWD, we have the GWD. While drilling, we TD the 12¼ we drop dual gyro at TD of the 12¼ So it's 3, 5, both are correct. So these are the tools that we had to achieve our objective for this well. And our workflow is very simple. Like I said before, we get the data from each tool, QC individually. If there is any corrections need to be applied on individual surveys, it gets done. And then we go to the our automated platform. And this is all done in real time in an automated fashion, where we ingest the data, either from the gyro or from MWD. We get everything ingested in real time. And as I said, the objective here also was not to add any complication to the drilling by taking the time, just do it on the fly in real time as well. And this was the key. So all this is, it shows here how the data flow from one box to the other, but the end goal here is, and the message here is, we just get the data, the fusion real time, and will be combined the dual link from RSS and MWD, IFR, MSA, SAG, we combine them with the GWD while drilling in real time on the fly. And as soon as we need TD and we run the dual probe gyro, we get the data and we combine it to deliver the final surveys at TD of the 12¼ before to use it as the tie-in for our 8½. So how does it look like when it comes to the uncertainty? What is the ellipse size for each one of those? How does it look like? And this is what it looks like. Looks very nice drawing. And I was working on this one And my daughter was sneaking a peek and she said, "Oh, wow, this is a nice art. What is this?" So I started to explain to her and she kept looking at me like some weird looks. And, and you know what? I just thought that this looks nice, but then she walked. I'm very happy to be here. When I explain this to you, it's very easy. I'm sure you will get it. You already know what I'm talking about here, right? And that's why we enjoy getting together and spend more time here. So the first survey that we have, this is the GWD, and it's highlighted more thick. Can you see it? This one here. This is the GWD ellipse, and it's all centered here. So this is the GWD, and we look at the other ellipse here, the magenta one. This is essentially the dual link, IFR, MSA, and SAG. And in real time, we combine these two together. And this is the ellipse that we end up with. I'm not, you can review the paper. I put the number at the beginning if you want to know the actual numbers and stuff. It is to get you an idea, relative, the sizes, how do they look like. And so the red one is essentially the combined position, average combined position of the GWD and RSS inclination, MWD, IFR, MSA, SAG. We TD the 12 1/4 at 25,000 feet. And then we run the dual solid state gyro. We drop it down, we get the data, and this is what it looks like. It's fantastic, it's good. It's actually very accurate. The only challenge here is we don't get it in real time, so we have to have also a solution in real time. So we get this EOU from the dual gyro, dropped dual gyro. And this one, you remember, this one, the MWD that we have. And we combine both. And this is what we end up with. If you remember from the first few slides, we talked about the challenge, that we're talking about 50 feet TVD, that we need to land with 50 feet TVD. Here we have it like 40 feet, 42 feet when it comes to the TVD. And this has been successfully placed geometrically at this ERD well, just relying on the expertise of the surveying, the knowledge of Wellbore surveying and tools and such, right? So we can do a lot of things. We're in this room here, a lot of things we can do, and everyone appreciates what we do. And there is a lot of unique solutions that we can come up with to show the value that we can provide. Now, this is when it comes to the position for the TD of the 12 1/4. We achieved, everything is good. We land the well, and then we need to drill the 8 1/2. It's very challenging when it comes to the 8 1/2 due to the fact that you already have well there, and there was an overfly. We had to go overfly of the old well and then go lateral parallel to it. So we had a lot of close proximity situation here. And this is what I'm trying to explain in this plot here. If we see this, so now this is the 8 1/2. It starts from the 25,000 feet down to TD. And what you see here, this is the separation factor. This is the scale of the separation factor, 1 up to 3, 3 1/2. And the green one here, so we started separation factor 3 at the beginning of the 8 1/2. And then we drilled until we came lateral. We did the flyover. So this is the peak of the flyover from the top. So this curve here is the incident angle between the two wells. I'll explain in a minute. So the green one first, you see the separation factor, it drops down significantly, right? Because in order to have these two wells parallel within 50 feet and less for reservoirs. So this was one of the constraints, one of the requirements. And I'm showing here the incident angle between the two wells because it's very important of the solution that we're doing right now in the 8 1/2 to mitigate the, not to mitigate, to minimize the collision risk and allow us to drill in close proximity, which is a passive magnetic ranging. So this incident angle, it shows how these two wells, two laterals, are reaching each other in reality. And the best case scenario for the ranging is when the two wells, they have an incident angle that is 0. This means they are parallel. So when the wells, they are parallel to each other, this is incident angle 0. When they are 90 degree, so the incident angle would show like 90 degree when they are drilling to each other. So the passive magnetic ranging, as you know, best case scenario, you want to be parallel to each other. And we're looking at how it's going to look like, and what is our chances of succeeding here if we're going to use this technology. We did a lot of modeling, and we looked at the incident angle as a piece of them. And we realized, okay, fine. So here we have a very good chance. And we did some modeling at the worst case when we have this incident angle that is around 25 degree to see how much of a signal that we can achieve. And for those of you who do not know what is PMR, which I doubt, you're all familiar with the MWD tool. Whenever we run MWD tool and we drill off the casing shoe at the beginning of the run, we will have bad surveys, and we wait. Typically, we wait maybe 30, 50 feet until the surveys are clean, and we start to use the surveys. And the same for sidetrack. If we sidetrack of the whipstock and what's not, it's the same issue. We cannot take MWD surveys. We cannot have a good MWD surveys. So these bad MWD surveys are actually good for ranging, because this external interference is the data that we get in order to define the relative distance and direction between the two wells. So essentially, we rely on the magnetization, on the magnetic features of the offset well casing. So the first, if I want to run this for collision avoidance, I want to make sure that my offset well cased, there is a steel there, and it has a decent magnetization. In this case here, we were faced with a challenge because the material that is used in the lateral that we want to drill close to, it has chromium, 13% chromium, stainless steel with 13% chromium, and there was a lot of doubts if this is going to be has any ferromagnetic features, characteristics we can range to it or not. So we worked with the operation team to get an actual physically piece of this liner, and we brought it into our shop to run the testing, a physical testing on this. And what you see here, you see what's hanging up here due to the shop limitation. So we got this liner, and it was actually hanged up the way that you see it with a lift, a crank lift here. And this is the MWD tool that we have with our engineers trying to assess what is the impact of, is it magnetized? Can we see anything, or it's actually just, it's just nothing we're gonna get, no signal we're gonna get out of this. And this is a material, it's a super materialistic stainless steel with 13% chromium. So we brought it in, we did the testing. And we looked at the data that we got, and based on the data that we have, we confirmed that it's magnetic, and we were able to pick it up on the MWD, and this is actually the actual MWD tool that we ran also. So to this extent, we did not want to leave any stones unturned, and we wanted to make sure that our success rates is the highest. So we did the actual test with the tool before we send it out to the rig. And the numbers that you see below here, it shows the distance between our tool. And now here we're looking at incident angle 0, which is the best case, right? And the distance between the two. And we see what is the amount of signal that we can get in order to use it for our modeling when we drill. And this will give us the best information to use in our model. So when we drill ahead, we're able to range to it and see how far is this well. And this one here, what it tells us in a nutshell, at 22 feet, we're able to see an interference of around 300 nanotesla, which is within the PDX criteria of the MW. So we can have good surveys, actually, less than 300 nanotesla, and we are maybe 30 feet from the other well. So we'll take this the other way around. If we see any interference more than 300 feet, for instance, 300 nanotesla, for instance, we know that we're going to be closer within 20 feet. So in this case here, we don't want to too close. We don't want to get close to 30 feet. I realize the time is almost up, but I know we have some time, right? So what we're saying here, we will do our ranging in this 8.5. We will monitor the data in this 8.5, and we will follow our workflow when it comes to the passive magnetic ranging for collision avoidance. And this relies, as like I said, on the MWD tool. We collect the data in real time, and we use a continuous definitive dynamic survey. So essentially, we get the data pumped up a good accuracy. We get it pumped up the 6-axis data. We can get it every 2 minutes based on the ROP that we drill at. So what we want, our objective, we want to have one data point, one survey data point per feet when we drill, or per 2 feet. Like we can, based on the studies, we can maybe up to 3 feet or 4 feet, we can have one data set. It should still be okay. So we stream the data, and again, operation constraints. We don't want to interrupt any of the rig time. And this is all done in the fly. And this is what it looks like when it comes to the signal. And it shows a very, very small interference here. So this signal here is a decomposed, the magnetic signal decomposed from the axial and radial. And you see like a very small signal that is even actually less than the 300 nanotesla. It gives us an assurance here that we are more than 25 feet or 20 feet away. So we're able to make sure that we don't get any closer. So the interference was limited until we TD'd the well. The liner has been run. This has been completed last year, mid of last year. And it has been on production, and it's been impressive for our operator to get the production back, and it has been very successful, and it's been a great success. To conclude here, accurate wellbore surveying is not an option, is not a luxury, is not a cost. It's essential for our operation. It has a lot of value. And this case here that you see, it shows the value very clearly. And it shows that as a group and as a community here, we can face any challenge, and we can come up with a solution to any challenge that we come across. So again, this has been placed successfully in real time without any interruption to the rig operation. And that's what I have. Thank you for listening, and I hope it wasn't too long.
5-minute cushion here, so we have time for a couple questions.
Hello there, I'm Chris graphics. So these error models that we're using, you have a weighting which depended on whether it's a component of the gyro or the MWD. Question is, are these weightings static for the tool choices, or do you envisage them being affected by dynamic factors, as well as that sort of thing?
It is, and you've seen on the this one here, it's actually a function of the Wellbore geometry, right? Like this one here. So this is an example of one weighting function for the MWD. And it does vary, because what you see here, it's relative to where is your azimuth and where is your inclination, right? So this is a weighting function. And in the best case scenario, you have two tools, same accuracy, you will have like a weighting function half and half, right? But now we know and we understand, based on the error model, based on the errors associated with the environment, like you mentioned, we have a deterioration in the azimuth of MWD, for instance, in east-west direction, and then you have less weight in these directions on the azimuth from the MWD, for instance, right? So it's taken into account. So the answer is yes.
Thank you for your presentation. You showed this pyramid that's not the threshold. That's that. And do you account for the external magnetic disturbance? Is part of the workflow?
It is.
Taking external, knowing it exists, and not that point, it's not related.
That's a good question. It is part of the workflow. It wasn't needed here. It was not used here. But if we suspect, if we have a situation that we suspect, and this is in a region where we need to monitor for it, it has to be monitored for it as well. Because we're talking about 300 this, we cannot, and even less. So that live part, if it's needed, definitely that's something we'll be used. By the way, this shop here, anybody guess where is the location of this shop? Where?
This country,
Huh?
this country.
This country? Which country?
Oh,
No, no.
We got a request to repeat the question.
Well, this was in UK actually, North Sea. So it's not far from here.
Yes, related to that also. So when you combine all the surveys, so you reduce the sensitivity, and you have a multiple level position of the world, which is the zone zero, then you reduce the. Once you will be doing 3 times sequencing, you will have a new position, which is relative to the first record that you want to reduce the position. So you have a new position relative to the first one, and you have a position which is the most probable position from one study. Which one will you be using? And I think it should be starting to go remotely, relatively, since you are doing testing. So are you still using the combining survey method when you are doing testing?
This is a very good question, and this is a huge question in the future. Right? Because the future is to integrate the PMR to this most accurate position, which is not done today. So we just rely, now you have, let's say, absolute position and you have a relative position. So today we're just relying on the absolute position for our purposes and using the relative position to give us an indication of how far from we are from the other one. Because the ranging data is relative, right? In the future, you could rely on the offset well position, the relative position, your position, and to improve further. But this is a good look into the future for sure.
And if you have the time to compare, looking at the graph, how about the position between
like it's well within the relative accuracy percent, so it's not far off, and it's all like lining in within the uncertainty that we put.
All right, I think we're comfortable.